So for the NAE Grand Challenge, we will focus on managing the nitrogen cycle. The nitrogen cycle is very complex with man-made and natural influences. One key aspect of the nitrogen cycle is nitrogen fixation, which can only occur through lightning in the atmosphere and nitrogen-fixing bacteria in the soil. However, in order to speed up the process of nitrogen fixation, fertilizers are overused, leading to excess nitrogen, which in turn causes ecosystem imbalance. So the focus of this design is to retain fixated nitrogen to limit fertilizer use. The reason behind focusing on this particular aspect of the nitrogen cycle is that fertilizer overuse has a substantial negative impact. So in general, plants are limited on how quickly they can process nitrogen for them to grow since they are dependent on how much nitrogen-fixing bacteria is around them. Thus, fertilizers are used to speed up the process of plant growth. However, one plant, the legume, is able to fixate nitrogen at a much faster rate due to a mutualistic relationship with bacteria. The legume releases flavonoid proteins that attract bacteria towards it. The legume then traps the bacteria in the root, creating a node. Thus, a nitrogen-fixing chamber is created since the bacteria get sugar for their service. The design I propose is a flavonoid panel which mimics the legume process. It will contain two flexible silicone tops that allow plant roots to pass through the center of the panel, where a ring of atomizers will spray flavonoid proteins into the soil surrounding the roots. This flavonoid-rich soil will attract bacteria to the panel, which will increase nitrogen fixation. These panels will be placed outside the new building under decorative flowers and plants around walkways. This design was proposed on the basis that current technologies focus on resolving fertilizer overuse by taxing fertilizers or using expensive software. However, this design is innovative in the fact that there is no current production of a panel that attracts nitrogen-fixing bacteria near plants. The closest technology involves the injection of the legume nodulation gene into other plants. So the design criteria used are size, location, durability, accessibility, and materials. The size is considered for if the design is too large or too small, it may prove ineffective for the building parameter. On location, the design must be effective by not impeding the flow of pedestrian traffic. The most critical criteria, durability of the design, is necessary to decrease cost and solve the unnecessary need for fertilizer. The longer the design lasts, the less money is wasted on fertilizer use. The design must be reachable for maintenance, but not for the general public for safety purposes, and the materials are key to avoid biological and everyday weathering. Using a weighted benefit analysis, a scale of 1 to 10 was used to quantify the design. On size, the design causes an issue due to the panels having to be quite large to cover the area under the plants. However, the design makes up for it in location because the panel is outside, it is virtually out of the way of daily building duties. The design also does the job in having a satisfying 7 out of 10 in durability since the flexibility of silicon decreases the chances of the plant roots breaking the panel. Likewise, the atomizers will be composed of steel or platinum since those are durable materials. The design is great at decreasing hazards since it is underground. However, maintenance is an issue since the panel must be dug up to refill the atomizers. The materials are once again appropriate to the environment and increasing longevity. All in all, the total evaluation of the design is acceptable at a total of 171 out of 247. Here are my references.